Hello, Mr. Claudia here. And before we go any further looking at trigonometry, we're going to pause and talk about 3D things and 3D shapes. So I always like to show this picture from The Simpsons. This was a big deal when I was in elementary school. There was an episode where the 2D animation of Simpsons was going to kind of transition or visit the 3D world. They were going to have this 3D kind of episode. So there's Homer in a 3D space. And that's a good intro to what we're talking about today. Like, what does 3D mean? Well, the first dimension is if we're talking about just a number line like this, right? You can imagine this is, this could be the origin here. This is the positive x direction. So if you can imagine like a kind of a length on the number line, that would be a 1D length. So we could call this O, we could call this A, so this would be OA, the line segment OA. Just remember that this arrowhead with X, this tells us that we're looking at the set of real numbers extending to infinity. So that's what you probably learned a long time ago in grade school. Then when you got to, later in grade school or high school, we taught you about 2 dimensions. Now 2 dimensions is when you have kind of a 2-coordinate system. So you have an x coordinate and a y coordinate, kind of like this Cartesian plane. And now if this is my origin here, you could choose some random point out here that has an xy coordinate, and I could connect those and make, this would be OA. And this point A has an x and a y now. And there's my point O. So in 2D space, you have 2 measurements, and the 2 axes are actually perpendicular to each other. So that's important to know. In 2D space, the x and y axes are perpendicular. Now, let's talk about 3D space. 3D space, we start the same way. So we draw our 2 axes that are perpendicular to each other. But now we have a 3rd axis, a 3rd coordinate. And you can imagine it's also going to be perpendicular to the first 2 axes. So it's going to come, if you can imagine, out of the page, right? Make some great illustration there. So you can imagine this 3rd axis. Now, we can't draw in 3D. This is a flat page after all. So I have to draw this kind of 3rd axis at an angle. So now you kind of are looking at this 3D space. You kind of have to use your imagination a little bit. We also tend to typically draw this as the up direction is Z, and then we have X and Y like this. X is the one coming out of the page. So this is technically the XY coordinate plane. So there it is, and that's the flat part. And then the Z, the 3rd coordinate, is going up. So now you can imagine, you have like a point, you can have a point in space like out here. And that point is actually, it's a certain amount along the x-axis. It's a certain amount along the y-axis. And then it's a certain amount up the z-axis. And so you can kind of get a sense that this length, this is O, and this is A, X, Y, and Z. So OA is now this 3D amount. It can be hard to understand. If you were taking a vectors course, we'd get into more about how to draw these. We won't do much of that now, although I will just kind of show you that it is easier to understand a 3D drawing, just for your own information, if you draw a box. So if I were to draw a 3D box, you can understand this 3D drawing a bit more, right? So you can understand that there's a 3D box there, and I'm going from this corner to this corner. And that helps me make sense because I'm drawing a 3D thing on a 2-dimensional surface. So in 3D space, the x, y, and z axes are perpendicular. We're not going to get too much into this, but your studies, if they continue in math, you'll start to look at 3D motion. Like it's not enough, or 3D 3D math. It's not enough to just look at 2D all the time, because say you're looking at how your knee moves as you're running. That's a 3D thing. It moves up, down, and side to side. You're flying a plane, up, down, and side to side. So 3D is part of your world. Eventually, calculus, if you keep studying calculus, eventually you'll have a section on a course on 3D calculus. Some of you might have come across 3D things already, especially if you're in physics. You might have done this with if you start talking about magnetic fields and some types of motion. Anytime we're dealing with 3D space, or these kind of three axes, we technically always draw the axes using the right hand rule. And so to do that, you use your right hand, and your first finger is the x-axis, your second finger is the y-axis, and your third finger, your thumb, is the z-axis. So if you do that, you'll always get the right orientation. If I kind of turn this, I have my thumb going up and my first finger going out. So that's the axis I've drawn. This is different than the left-hand system, which this is x-axis would be backwards. So things that we do that you'll be studying that are 3D, you're always going to use the right-hand rule. So that's about really all we talk about in terms of 3D, although there are two formulas that we're going to be using, and these are both on your formula sheet. One thing would be to find the distance between 2 points. Now, we're not going to spend a lot of time talking about where this comes from. Suffice to say, it's very, very similar to the to a formula you did for 2D, the distance between two 2D points, which you did in grade 10 in the analytic geometry chapter. And it has a lot to do with the Pythagorean theorem. So there's the distance between 2 points, 3D points in space, and the midpoint between two 3D points. I have another formula, looks very similar to what you did in grade 10. So we're not going to talk about where these come from too much. But I just wanted to show you them there because they are on your formula sheet. So these are the distance between 2 points, x1, y1, z1, and x2, y2, z2, and there's the midpoint. So let's just do a very basic question. Again, this is in IB, and it's not kind of too out there, but we should just kind of make sure we're all familiar with it and we know what's going to be on the exam. So here I have the cuboid shown at the right. So this is a cuboid, or it's a rectangular prism. AB is equal to 6, so this length is 6. AD is 5, so that would be this length here. See how easy this is to do when you have a box? It makes things a lot easier to understand in 3D. And AE is 2. Oh, that would be this length here. So can you find the coordinates of each vertex? Well, absolutely we can. I mean, A is at 0, right? It's where Z is 0, Y is 0, X is 0. So for part A, I have A, 0, 0, 0. B would be 6 along the X direction, but then the other two are 0. What about C? Well, that would be 6 along the X direction, 5 along the Y direction, and then 0. D is going to be, okay, it's 0 in the X direction, 5, and then 0. E, I guess I'll just do them all here. E is going to be 0, 0, 2. F is, okay, so F is 6 along the X, and then 0, and then 2. G is going to be 6, 5, and 2, so that's kind of done all of them. And H is going to be 0, 5, 2. So you have a little bit of spatial awareness. You can figure out the coordinates of each vertex. Now, can we find the midpoints of EH? So I don't know, however you want to say this. EH, midpoint. Well, to do that, I need to use my formula here. So I need to take E and H and add the X coordinates. So 1 and, or 0 and 0 and 0. divided by 2. Then I take the y coordinates, which are 0 and 5. And then the z coordinates, which are 2 and 2. And so that gives me 0, 2.5, and 4 divided by 2 is 2. Does that make sense? Well, if you can imagine, EH is this line here, so the midpoint is right there, and of course, yes, it would be 0, 2.5, so halfway, and then it goes up 2. So you can actually figure it out kind of just by looking at it, but we can use this formula as well. Finally, part C, I want to find the length of AG. Well, AG is this distance here. Again, it helps to have the box, you can kind of imagine it. What's the distance of that, or what's the length of that, that line? Well, we need to use the distance formula, so I need to subtract, if you go up there, subtract the x-coordinates. That doesn't really matter the order as long as you're consistent. Actually, it doesn't matter the order at all, but we'll take the g because they're positive numbers and a is just 0. So g is going to be 6 minus 0 squared plus 5 minus 0 squared plus 2 minus 0 squared. Don't mess up this simple formula. Make sure you're putting this, you're adding up all these amounts. So I end up with 36 plus 25 plus 4. What's that give me? 40 square root of 65. That's a nice answer. Don't need to use a calculator. Nice exact answer. So that's just kind of an extension of what you did in analytic geometry. And it doesn't get too much more difficult than that when we look at the coordinate planes. So that's kind of just an introduction to 3D and vectors, which are no longer part of the IB curriculum, sadly. So our study of 3D space does not go much further than what we just looked at, but you can still expect to see questions involving 3D shapes. Now, some of this you've probably done way back in grade 9. Again, it's not the most difficult concepts, I just want to go over them really quickly. So just a few definitions. A tetrahedron, that's a figure with 4 sides. They could be all sorts of different sides, but that's the general term. A right cone or a right pyramid, this is where you have, there's a right angle. So if you dropped a height from the very highest point, it would be a right hand angle, and it would come down to the center of the base. So it's kind of like a nicely shaped cone or a nicely shaped pyramid. And a hemisphere is half of a sphere. That's a useful thing to know. So for all of these shapes are what you could see in an IB test or exam, and you've probably seen a lot of them before. These are the formulas that you're given too, and these formulas you'll find on in 2 parts of your formula sheet, so do not memorize these. If this is my formula sheet package, prior learning, these are things you should have learned before coming to IB. Sure enough, oh, there's the distance between 2 points, look at that in 2D. But there's the volume of a prism, volume of a cylinder, volume of a cuboid. So those 3 here, right? You should know these volumes. You probably don't need your formula sheet, but there they are. They're on your formula sheet. Then if you flip ahead to the section with trig, the geometry section, there you have some of the more advanced areas and surface areas and volumes. All of these are on your formula sheet, and I've listed them here for you. So right cone, sphere, right pyramid. I wouldn't expect you to memorize these. They're on your formula sheet. I wouldn't expect you to really know too much about them, but there they are. So the volumes of each of those. And there's the area of the curved surface. So, you know, often you'll have questions where you have to look at surface areas. So the cylinder, we don't tell you the surface area. We tell you the area of this curved surface. Same with the right cone. We don't tell you the area of the whole thing. We just tell you the area of the curved surface, sphere, and right pyramid. We don't tell you. You'd have to figure that one out on your own. So we're going to do 2 examples just to see, to kind of see that you're comfortable with these concepts. Again, we've done these before, but we'll quickly go through them. First question. Calculate the volume and surface area of the following shape. So I have some sort of cuboid, or it's like that's actually a cube, exactly. 6 centimeters on each side, and then you have some sort of right cone that's been subtracted. So you can imagine the volume, you're going to take the volume of the cube and you're going to subtract the cone. So let's start with that. So this is 9 or 10.2, page 3. And this is example 2. Okay, so we want to look at the volume. Let's start with the volume of the prism, or the volume of the cuboid, whatever you want to say. So that is a length times width times height. Probably don't need my formula sheet for that. That would be 6 times 6 times 6, which is 216 centimeters cubed. Then we have the volume of the cone. That one I don't really know, right? And I don't expect you to know that one because I have a formula sheet. A third pi r squared h. Third pi r squared h. Be careful here, make sure you use the right numbers. A third. The radius is 2, it's half of 4, so it'd be 2. And the height, well, it would have to be 6. It looks like it's as tall as the cuboid, so it'd be 6. So that gives me an answer of 2 times 2 times 2, which is 8. Is that correct? Sorry, 2 times 2. Yeah, sure, 8 pi. Did I do that correctly? Sure. Okay, and then I also need, okay, so now I can find the V total, the volume of the box in total, which is the volume of the prism, subtract V cone, and so I had 216 minus 8 pi. I'm pretty happy with that answer. If you really wanted a number that you can tell someone, and I end up with approximately 191 centimeters cubed. Wow, very great. Okay, now if I wanted to find the surface area of this this shape, you have to imagine a little bit more, right? You have to kind of, okay, add up all the sides, the bottom, then you have to add the top, but then subtract this part that's missing, and then you have to add in the side of the interior here. So, you know, when you're thinking about surface area, it's useful to kind of mentally unfold the shape, and you'll kind of reduce it to its base areas that you can then calculate using your, length times width and area of a circle. This is one kind of neat demo that I usually do with my students. Is just when we talk about a cone, like this is a hard one to unwrap, right? A cylinder, when I unwrap it, it's basically a long rectangle and 2 circles. I mean, there's the illustration there. And you can actually figure out then the area of the long rectangle. I mean, the length of it corresponds to the circumference of this circle, which is 2 pi r. So the area of this curve stretch is 2 pi r h. But the cone is a lot more difficult to understand. And one way I like to show students is if you cut out like a Pac-Man from your from a circle. So you basically take a circle and cut out a sector, that forms a cone, a right cone. It's hard to see because you're looking at it from a video. And then if I cut out more of that Pac-Man, I would have folded it in more, and I would have had a smaller cone, or a kind of a cone with a higher angle. And there you see there. So the area of a cone is really the area of a Pac-Man. We're going to talk more about this when we look at radians, but basically this is the area of a circle, pi r squared, with a sector removed. So the formula for that area is pi r l, where L is the length of the cone. So that would be L there. Okay, so let's get to work. We want to figure out what the surface area is. So let's start with the surface area of a side. That would be length times width, which is 6 times 6, which gives me 36. Now, I want to figure out the surface area. Again, you guys might have a slightly different method. I want to find out the surface area of the circle, which is pi r squared. In this case, it's pi times 2 squared. So that would be 4 pi. And then I also need the surface area of the cone, right? Because we've talked about now the surface area of each side, the surface area of the circle, which gets subtracted, and then the surface area of the interior bit, the cone, which is like some extra surface area. So that would be the formula, where is it? Pi r l. Pi r l, which is pi times 2 And for the length, well, it just so happens I don't have the length. I don't know what this diagonal length is. So what I'm going to have to do is actually, let me draw a little sketch and see if I can figure it out. So this is my cylinder, or sorry, my right cone. Let me get a different color here just so it's more clear. This radius is 2, and if I drop a height down, I know the height is 6. So then, and then this length is L, and that's the thing I'm trying to find. Well, I can use the Pythagorean theorem here. L squared is equal to 6 squared plus 2 squared. L squared is equal to 36 plus 4. So L is equal to square root of 40. So let me just put that off to the side here. So then, when I sub that in, now I have root 40. So my surface area for the cone is 2 pi root 40. So now if I want to find my total surface area, well, that would be 6 of the sides minus the surface area of the circle plus the surface area of the cone. So this gives me 6 times 36 minus 4 pi plus 2 pi root 40. This gives me 216 minus 2 pi plus 2 pi root 40. That's getting a little messy there. Let's try to use the calculator to clean that up. So I get 216 minus 4 times pi plus 2 times pi times root 40. And my answer is 243 centimeters squared. So this is a little bit of reasoning, a little bit of thinking, but it's if you're careful with the formulas and careful with the formula sheet and your kind of your diagram, you should be able to get through these questions without too much of a struggle. Let's go to example 3. Okay, and this is a good example of a question that involves trig and 3D shapes. So you have the Louvre Pyramid. So this is a slightly controversial geometric kind of new modern design they put in the center of this museum, this very kind of traditional museum in Paris, but it's kind of cool. So it's a right pyramid. It has 4 sides on the bottom, and then it comes up to the top like that. It reaches a height of 21.6 meters, and its square base, each of the sides is 35 meters. Find the angle between a face and a base, and then find the angle between the edge and the base. So if you can imagine, this is a face, and this is an edge here. And really, this is, again, not the most difficult question, but it's a little tricky to imagine what the question's asking for. So let's go down space here. So for example 3, so let's do part A. Can we imagine this? Let's try to draw a sketch to imagine it. So they're saying we want to know the angle with the face. So if you can imagine your right pyramid, if we were to drop a perpendicular, if you put a sideways view, if I were to look at it sideways, I have this shape. Where this is a face. Now, if I was doing that, the base then would have a length of, we said it was 35. So this length here is going to be 35 divided by 2, which is 17.5. And the height, we already were given in the question, this was 21.6. So if I want to find the angle between the bottom and the face, well, I can do that using my primary trig ratios. Which ratio involved for this theta? This is the opposite, this is the adjacent. So that's tan theta is opposite 21.6 over 17.5. Now just to remind you how this is done, 21.6 divided by 17.5, that gives me the ratio of opposite to adjacent. It's 1.2343. You don't have to always show all this work. To find theta then, to find that angle, I have to take the inverse tan or the arctan of that number. So I press shift, press the tan button on my calculator, and it's going to give me that angle. 50.8986, which is rounded to 3 decimal places, or 3 significant figures, is 51 degrees. Now for part B, they are asking for the angle between an edge and the base of the pyramid. Okay, so what helps maybe here is to draw like a little sketch again. You can imagine, maybe imagine like this 3D shape, right? So this is my, you know, that's my base, and you can kind of imagine there's the height of my pyramid, and there's the edge. So I've tried to draw like kind of a 3D shape, and that's a right angle. This helps me understand a little bit what I'm trying to figure out, right? I want to find out this angle, which we'll call beta. This height is still 21.6, but now this length is a little bit different. I kind of need the diagonal length. If you want, you can rewrite this, or we can draw a view from above. We know that each of these sides is 35 and 35. What we're actually interested in is this length here. I would call this the, why don't we call it the diagonal? Why don't we call this full thing D? And then essentially we need half of it. So how do I figure out what this length is? Well, look, this is another right angled triangle. So I would say D squared is equal to 35 squared plus 35 squared. Oops, sorry, you can't see anything I'm doing here. So D is equal to, what's 35? 35 squared times 2, so the square root of 2450. So that's what this whole length is. So this here then is D divided by 2 is equal to half of root 2450. So now if you use your primary trig ratios again, you have tan beta is equal to opposite 21.6 over half of root 2450. So this gives me, and again, you don't have, you can do this in one swoop. So we can go 21.6 divided by 0.5 times square root of 2450, and then I take shift tan of that answer to get a beta or a beta of 41.1 degrees. Does that answer make sense? Yes, the angle between the edge is a lot kind of sharper than the angle with the face. So it's sort of an annoying question. You really kind of have to imagine this this shape. You almost have to be able to imagine it in your mind and turn it around and look at it in your mind. So it helps to draw sketches. It helps if you can draw sort of a 3D sketch to help you to imagine the question you're looking at. So that is it for 3D shapes. Hopefully those aren't too stressful, or it's not going to be too challenging. There is no practice in your current textbook because this is something that was added into IB in the latest iteration. I have given you some extra 3D shapes homework, and I've circled the questions that I think are relevant. There are not that many, and most of them are actually kind of the exam style or a little more challenging in the answers. So you'll have a chance to get a little bit of practice. Good luck with that, and we'll see you next time.